This is the third video about resolving vectors, and we're resolving the vector into its rectangular components here, and this builds on the first couple of videos. We saw previously a situation where we have vector A, and we're looking at resolving it into two vectors, u and w, and they're in regards to a vector B. U is parallel to B and w is perpendicular to B. And we derive these expressions here, and so we saw in our recent video the vector resolute is given by these expressions. So far most commonly we've used the first version of that. They're all equivalent to each other, they're just manipulated in different ways. So it would be correct to say that vector A here is vector u plus vector w, using our geometric vector addition. So to rearrange that, vector w equals vector A take vector u. Now vector u is expression we just alluded to is up here, so that would be the same as vector A take A dot B over B dot V times vector B. So that gives us an expression for the perpendicular component. Perpendicular component. So I've just titled or given each of the results a number or a title, and so if we sub result 2 into result 1, we get the following here for A if we want to resolve A. So we have there's u, you might remember that from not very long ago. So we have u dot b over b dot b times vector b minus, or plus, sorry. Now there's an expression there for w, so this w is going to be replaced by this expression for w here. So just to be more explicit, that is being expressed as this, and this one is expressed as that one. So writing all that in, just grouping those, tidying it up, and we have our expression that we need now. So that's what we use when we resolve our vectors into rectangular components. So that's essentially what we use. So make note of that. Showing this with an example, resolve the given vector I plus 3j into rectangular components, one of them which is parallel to another given vector 2i take 2j. So let A equal I plus 3j, and let B equal 2i take 2j, 2i take 2j. Let's calculate the vector resolute of A in the direction of B, and that's what we were just looking at before, and so that would be u equals A dot B over B dot B times B vector which equals the following. Once we work out the dot products, you can see them there. So we've got negative 4 over 8 times vector B 2i take 2j. So it's basically negative a half of each vector, so it's negative I plus j. Whoops, that's a j. That's a j. So we've got the first part sorted. Now we've got to find the second part, perpendicular resolution of it. So the perpendicular component, so putting that in, and it's a take away that resolute, and it's a take, use brackets I would suggest, so we get our signs right. And vector A just above was I plus 3j, so we have I plus 3j. That's all that got a little bit of stray down there, didn't it? Okay, and I plus 3j take negative I plus j. Be careful here with this sort of stuff. That's I, you got your components there, that's minus negative I, so that's plus I, so it's 2i, I plus I for an I? No. So 3j take away 1j is 2j. 2i plus 2j. Therefore, the given vector A, which was I plus 3j, equals, broken into components, I plus j, which was up here, and the perpendicular component, which was here, and that should be a case of left hand side equals right hand side. And we can do a quick check. Yep, the I's check out, and 3, 1, 2, yep, they check out. And another way of checking it is that basically the perpendicular component and B should be able to be dotted together to give 0. Okay, so B was there, and right down the bottom I've done a check. The perpendicular component dotted with B, and it's commutative, so it doesn't really matter which way you do it, but you can see that's 2 by 2, which is 4, 4 plus negative 4, which is 0.